Hello everyone, we are now going to the pitch poster session. It will be a very, very speedy session, 5 minutes or 4 minutes for each participant. And at the end, those that don't go by bus to the dinner, please pay attention that you should be there before 7:30, since the show there begins at 7:30. The others should be in front of the hotel to pick up the bus at 7 p.m. So I would ask for the speakers, for the poster presenters to come to the first row, please come. We have 7 presentations, so we have to move on very quickly. So the first one is José Castanheiro. I won't present everybody, since otherwise we should not have the time. So please go ahead. The floor is yours for your 4 to 5 minutes presentation.
Qual é que é o seu? Desculpe. Este? Este aqui?
Thank you, Professor Paulo Ferreira. Good afternoon, everybody. The aim of my work is acetylation of cineol with acetic anhydride over zeolites. The cineol is a compound from eucalypto oil. It can be transformed into acetates using traditional inorganic acids. But due to the environmental problems, the homogeneous catalyst should be replaced by the heterogeneous catalyst. In this work, you try to use zeolites. Zeolites are aluminosilicate crystalline. The catalyst, these zeolites can be used at petrochemical industry and fine chemistry. The zeolites used are beta zeolites, OSI zeolite, and ZSM5 zeolite. The beta zeolite was prepared on the lab by my students, and the other zeolites were by zeolists. This work is in the beginning. The catalysts were characterized by nitrogen adsorption, isothermic, and X-ray diffraction. In the reaction, the reactor was loaded with acetic anhydride, cineol, and zeolite. The reaction were carried out at 60 grams. This is our characterization. The zeolites are microporous materials, have a high surface area. After the preparations, the structure are similar. There are no observation some change. And when we use on the catalyst, you can see the beta zeolite show high catalytic activity, while the ZSM5 have the low catalytic activity. Maybe it could be the low surface area and porous volume. And sometimes it's possible there exists some internal diffusion limitations inside of porous materials. The selectivity to monoacetates and diacetates are in the picture. You can see the zeolite with one show high about 80% selectivity to monostates and 20% to diastates. In conclusion, it's possible to carry out the acetylation of cineol with acetic anhydride over zeolites. Beta zeolite showed the highest activity. However, OSI zeolite 1 show greater selectivity to monostates. This is, as you tell you, is the beginning. It's work very in the beginning. In the future, it's important to characterize the acid strength and distribution, study the catalytic stability of these materials, and characterize the materials after the reaction. Okay, thank you for your attention.
Thank you, José. It's now time for Sónia. Sorry, but we don't have time to questions. These are the rules. Please take 4 minutes if possible, or less.
Isto? Ok, Sónia, corra bem.
Just a minute. Hello, everyone. My name is Sónia Figo from the Biomass Center for Energy. Today, I'll be sharing our work title, Assessment of the Production and Sustainable Availability of Residual Forest Biomass in Maritime Pine and Eucalyptus stands. Residual forest biomass, or RFB, plays a key role in Portugal's decarbonization and renewable strategies. It's a renewable byproduct of forestry operations that supports clean energy production, helps reduce wildfire risk, and adds value to local forest resources. Our study aimed to quantify this resource accurately and ensure it can be mobilized sustainably. Portugal forests are mainly composed of maritime pine and eucalyptus, two productive species regularly managed through thinnings and harvesting. To use this biomass effectively, we need to know how much is available, where it is located, and under what conditions it can be mobilized. Our objective was to develop a replicable methodology to quantify and map RFB production, ensuring both environmental and logistical sustainability. This framework provides a solid technical basis for better decision-making in energy planning and forest management. We combine field inventories, dendrometric measurements, and weighing trials conducted in pine and eucalyptus stands. These data were used to calibrate biomass equations and update forest harvesting models, allowing us to estimate annual production factors per region expressed in tons per hectare year. We then applied these factors to the forest areas in the most recent land use and land cover map of Portugal to calculate the theoretical biomass production for each region. To ensure sustainability, we apply a 70% utilization rate, account for topography, accessibility, and environmental constraints. Our analysis shows that the theoretical national productions of residual biomass is about 3.1 million tons per year in green rate. After applying the 70% utilization rate, the sustainable availability is approximately 2.2 million tons per year. Regional variations reflect differences in climate, soil, and management practices. These values represent regional annual averages and can slide between years. The mobilization of biomass depends on accessibility, logistics, and competition for resources. These aspects must be considered in planning and land use analysis to avoid conflicts and promote integrated forest management. Overall, our results provide a valuable insight for regional energy planning and wildfire risk mitigation, offering guidance for policymakers and investors. In conclusion, this study presents a replicable framework for estimating regional residual forest biomass in Portugal. It supports the bioenergy strategies, sustainable forest management, and climate policy goals. However, results must be interpreted considering regional variability and logistical constraints that influence biomass mobilization. Taking these aspects into account is essential for integrate forest management and for preventing resource use conflicts. Looking ahead, we plan to integrate remote sensing, machine learning, and update forest inventory data to improve predictive capacity and optimize research planning. Thank you for your attention.
Thank you, Sónia. You took 50 seconds more than expected. It's now time for Carolina.
Good afternoon. First of all, thank you Tecnicelpa for the opportunity, and thank you to Navigator Company for the collaboration in this project. I will talk about a poster that we have outside, so for more details, because we have only 3 or 4 minutes, please, if you have any questions, we can go there and we can talk more about it. But giving an overview, what was the project, what was the context and the targets. So the target was to build the APC in the bleach plant. For sure, why the bleach plant? Because it's one of the areas in the pulp mills that is consuming more chemicals. It's a continuous process that it's easier to integrate stage by stage, building an MPC control that is model-based and is predictable what is happening in every stage. But what was the special situation in this project was not only because we focus in instruments that is normal in APC, but because of some challenge that we have in Iberian market, we have to learn from the data and adapt the controls to be able to bring all the time the best result to the mill. Considering that, so a part of predict the results or stabilize the brightness, that is the main target, we were trying to understand what was the best conditions for every situation at the mill. Considering that we can say that we have 6 big points in this project that make the difference. So first of all, we can talk about operations, and it's a kind of change mentality in the mills that there are always budgets for chemicals, and there is always some restrictions from the mills that if you want to cross that line. But in this case particular, we save chemicals crossing that line, not all the time, but often, because if you don't cross that line, the controls start to saturate and you cannot go out of that. So this was one of the points. The other one, and we have here 4 stages about pH, and I will try to resume all of them. One is the bleach plant is running with medium consistency and quite high. We can talk about 7 to 10% consistency, and most of the pH are not performing well in that range. So we need an extractor to be able to have a continuous measurement that we can reliable, which means it's not only the result, because for sure in DCS we had the number, we have the result, but that result was not giving us any information to build a control. A part of it was, okay, now we have a good measurement, let's integrate this in the control and start to see that number with the value. And not only that, but we were able to integrate the inlet and outlet pH of different stages, and inside the MPC we were able to reduce the variability in 10% more, which was giving the pH control on target that we want, optimizing every stage. We did not only for alkaline stage, but for acid as well, and we were able to reduce the variability. I will show the results later. The other point that is not about pH, it's about the brightness itself. Due to some challenges at the mill, was needed to integrate not only the final brightness of the final stage, but the drying machine brightness, which is in a different area, so different control room, but integrating everything, we were able to reduce not only the variability on the D2 stage brightness, but really the final brightness that is the quality parameter from the mill to the market. I will show just 3 slides about some results of what I explained before. The first one, as you can see, this is about the caustic, was the manipulated variable that we opened the range to be able to run always optimal. If you see, we were not passing the first high limit almost in the time, but for some conditions was really needed. A part of it, we can see the pH. The first graph is before install anything else, and you can see that the inlet and outlet pH are not correlating, and each one has a different behavior. After integrate this instrument and in the control inside the MPC, what we can see is a behavior between inlet and outlet pH that we can trust in both, and we can win the delay of the stage. So every change that we have in the inlet pH, we can see immediately and react in time to minimize the variability. In the last one, we can talk about the final brightness in the pulp machine. So between the 2 red arrows, you can see the limits defined by the operator. And before, you can see that in dark, you have the brightness variated when was manipulated by the operator. After, with the control, we start to minimize the range was possible because the standard deviation starts to decrease and we start to work more inside the range, not only in dark, but in blue, that is the final brightness. And this is the real target of the mill. Considering that, some results, and here we can talk about not only safe chemicals for money, but you can talk about safe chemicals for sustainability as well. So we were able to reduce the chlorine dioxide 9%, the caustic almost 18%, and the final brightness variability close to 30%. Not only that, but with all this stabilization of the pH, we can say that Cassia now is really in a high level on the benchmark. The benchmark usually a pH has a 0.25 standard deviation, but Cassia now is running even with lower than this with the optimization across the time. A part of it, we can say that with instruments measuring well, with a full team working for a success, we were able to use the MPCs and balance the costs, quality, and sustainability in every company. Thank you.
Thank you, Carolina. Allison, please go.
Allison.
It's the one.
This one. Okay. Okay, good luck.
Perfect. Thank you very much. Good afternoon, everybody. I hope you can hear me well. So I'm Allison Vercasson, and I'm working as a postdoctoral researcher at the University of Aveiro, at the CISECO Aveiro Institute of Materials, and today I will present you quickly the work I present in my poster. So this work is entitled Novel Thermoplastic Blends for the Development of Cork-Based Composites. For the general context, As you may know, a lot of plastic is produced every year, up to around 400 million tons annually, of which most of it end up in the environment, causing a lot of issues regarding pollutions, and predictions show up to 12 billion metric tons of plastic waste by 2050, which is a huge issue that we need to tackle. And one way to tackle it is to develop sustainable materials that are bio-based and biodegradable, that can substitute conventional plastic, but without compromising the performance. And one solution lies in the use of resources from forests that are renewable to produce greener composites. As you may know, Portugal accounts for 34% of the world's cork oak forest, which basically is a key in the vision of using forest resources to greener composites, as we have cork as a renewable source that is natural and possesses a lot of different properties, such as is lightweight, is hydrophobicity, but also it is chemically stable. So the use of cork for the production of cork composite would help to add value to this forest byproduct. To do so, we need a polymer matrix, but if we keep in mind this sustainability, we need to have a polymer matrix that is also bio-based and biodegradable. And that's where PHB comes in. PHB is polyhydroxybutyrate. It's the most available PHA. It's biodegradable, biocompatible, but it possesses, of course, drawbacks that are its high cost and its property, because it's very brittle and it possesses a very narrow processing window. So if we want to have a great polymer matrix, we can think of PHB blends to produce blends of PHB with other biocomponents, a plasticizer, another biopolymer, so that we can reduce the cost and at the same time, obtain improved and tunable properties. That will allow us to have a balance between the cost and the properties of the polymer matrix, raising our main research question, that is, what is the impact of the composition of the blend on its properties for cork-based composites. The approach we undertook in this project was first, of course, to produce the blends. So we used PHB as biopolymer matrix, then we used alginate and LO as other biopolymer and plasticizer. And the blends were produced by melt mixing and injection molding. Then we characterized all the samples with different techniques, and finally we were able to study the composition properties relationship. Here is a little overview of the key takeaway that I present in my posters. In my poster, I won't go into detail because we don't have a lot of time, so if you want to know more, please come talk to me tonight or tomorrow, or come to my poster. Thank you very much.
Thank you, Lisa. Thank you. You just kept the time. Thank you very much. It's now time for Patricia.
This one?
Yes.
Okay, good luck.
Thank you. Hello. So today I will represent you a little bit of our work that we do at the Pulp and Paper Institute in Ljubljana, Slovenia. This is a part of Prima project of Volpec, and I will talk about rice straw fibers as a sustainable alternative for paper and packaging applications. So growing environmental concerns has positioned natural fibers as a compelling alternative. Fibers derived from the renewable resources are abundant and fast-growing byproducts, making them a low-cost and eco-friendly input. So to mention molded pulp. Molded pulp was used for simple protective packaging, but modern molded pulp technologies now enable the development of food-grade containers with enhanced strength, thermal resistance, and, of course, water repellency. So what did we do? First, the rice straw from Spain was cut into 3 centimeter chips and then cooked in water for 3 hours on 110 degrees. Fibers were then pulped, washed, and screened to remove oversized clumps. And then pulp was diluted, mixed with starch and sizic agent to improve strength and printability, and then processed on a sheet former. A 1% fiber suspension with 70% of rice straw and 30% of long fibers was then drawn through a 3D printed mold with vacuum suction, and the wet layer was then transferred to a heated aluminum mold. We did the same with only eucalyptus fibers and long fibers to then see the results. I gave around one of these molded pulp cups. One is the one I mentioned, 70-30, and the other one is made 100% only from rice straw fibers. Okay, more than double the burst index was seen with the rice straw fiber sheets, and along with the higher elongation, the tear index values were equal with the eucalyptus and rice straw fibers, and the rice straw achieved much higher opacity but significantly lower brightness due to the unbleached pulp. In molded pulp cups, rice straw fibers provided better tensile strength due to the finer, more intertwined fiber forming, and compression results were similar, suggesting bulk density and mold geometry dominate compressive behavior. The dotted line is the rice straw fiber, and the straight line is eucalyptus fibers. So to conclude, rice straw thus presents a strong renewable alternative to wood fibers for sustainable packaging, though its low brightness may limit use in whiteness critical applications. That's all from my side. Thank you.
Thank you, Patricia. You were the best up to the moment. It's now time to Sakari, please.
This way. Yeah. Okay.
Okay, hello. My name is Sakari Toivokainen from Toihan. I want to present this kind of research that we did. So we wanted to know if we can estimate biosludge settling properties based on microscopic images, of course, with little help from computer vision. So here is example of biosludge. This is if you would be a laboratory worker who looks images daily basis, you would see that this is quite good actually. But then when we get this image analysis out of that, we can see different things as Heikki presented in earlier papers. But in this study, we wanted to know if we can use how much there is filaments and what kind of flux there is. If there is lots of flux on a porosity, low porosity or density, high density, this kind of biomass would most likely settle well. So we use this kind of model that we have created, and here is 3D model. This is example of a well-settling sludge and porosity. You see that most of the flux are low porosity level. And then when we increase or have a higher SVI, meaning it settles not that well, so we see that this distribution goes to different kind of, this is quite not that well settling sludge, and this does not settle at all. So we use this model. There was, by now there is 540 different sample sets that we have used to train this model. And then we use this complex model of porosity and linear model of filamentous bacteria. And then we had 45 new samples that were not used to train the model. And here is the results. Here is predicted, SVI, and measured. So with this low amount of numbers, 540 samples, we can get already quite good prediction how your biomass would settle in secondary clarifiers just based on microscopic images and computer vision analysis. Yeah. So the question was that can it be predicted or estimated from images? It can be. Yeah. Thank you.
Thank you, Sakari. Thank you for keeping the time. It's now time for José, the last but not the least, our last presenter this afternoon. Thank you, José.
Okay. Hello, everyone. My name is José Miguel Matos. I'm a researcher at CENTI, and today I'm going to talk to you just about a little portion of all the work that we have been developing in the scope of the BEAT project. In particular, I'm going to talk to you about a study that we made comparing two different solvents for cellulose regarding the production of man-made cellulose fibers. The BEAT project, I'm not going to spend much time talking about it. My colleague that is standing right in front of me has already talked about it in a presentation earlier today, so if you have any questions, we can talk later. Okay, now, what about the results I'm going to talk to you about? Sorry. What we did was to compare the dissolution using two different direct solvents for cellulose. On one side, we have NMMO, which is widely accepted and non-toxic solvent for cellulose, which is, like many of you surely know, used in the lyocell process. And the idea was to compare it with an ionic liquid. In this case, this one that you see here, that's pronounced ethylmethylimidazolium octanoate. Yeah, did you get it? Okay. Now, then in the end, you'll have to say that to me. And what we did was to compare them in pilot scale. I mean, not bench scale, but pilot scale, not big pilot scale, small pilot scale, still pilot scale, okay? And what we saw that in order to achieve complete dissolution of, and achieve a solution of 10% concentration of cellulose, we saw that we spent roughly the same time for dissolution, but we achieved that using substantially lower temperature when we use the ionic liquid. And this is very interesting in terms of energy consumption when we think about scaling up, right? So then we took these solutions, and what we did was to spin them into fibers in also a pilot scale spinning unit and under the same parameters. And what we saw was that we got fibers in the end that had higher tenacity when we used the ionic liquid in comparison with the conventional lyocell fibers, although elongation was a bit lower. Another interesting thing that we saw was that the fibers were substantially brighter when we used the ionic liquids as a solvent. And this is also interesting when you think about energy and chemical consumption in the bleaching of these fibers. So what do we want you to take away from this? Basically, in our opinion, we are talking about very promising alternatives for next generation solvents for cellulose when we talk about ionic liquids in particular, and in this case this one. We see that we were able to reach higher tenacities and higher brightness and effective dissolution. However, what I also want to say to you that this is ongoing work, and we are still working on some details. For example, the reuse of ionic liquid that has to be considered when talking about scaling up the technology. And I think I had to be fast, so so if you have any questions, please feel free to talk to me or my colleague. Okay, thank you.
Thank you, José. We reached the end of this pitch poster session. Let's thank our 7 poster runners and for keeping the time. And please gather there for a picture. Yes, please. A big applause for all of them.